Okay, so we're going to be going over implicit derivatives today. Okay, but we're going to be using implicit to do problems that we've absolutely have worked before. Tangent line problems, normal line problems. Okay, so we're going to be doing the exact same thing we've been doing before, just with implicit differentiation. So the first one says find the equation of the tangent line at 1, 2 for this ellipse. Okay, so if we're finding the equation of the tangent line, that's this equation, y minus y1 equals m times x minus x1. Okay, so to do that equation, we need x1, we need y1, and we need the slope. Okay, well, x1 they gave us. Since they gave us this coordinate 1, 2, x1 is 1, y1 is 2. Now, the slope is nothing more than the derivative of the function. So in this case, we need to find dy over dx. Okay, so we come over here to our ellipse equation, and we need to find the slope of this ellipse at the point 1, 2. So the first thing I'm going to do to make my life a whole lot easier is I'm going to multiply everything by 16. So I'm going to distribute it in, multiply both sides by 16. And of course, 16 divided by 2, I end up with 8x squared plus 2y squared equals 16. Okay. Now, since I got rid of all of those fractions, I'm going to take the derivative with respect to x to both sides. So the derivative of 8x squared is 16x, plus the derivative of 2y squared is 4y, dy over dx equals 0. We solve for our dy over dx. We move this 16 over, we get negative 16x over 4y, which simplifies down to negative 4x over y. Okay, so that is our derivative. But now we need to find the slope at the point 1, 2. So we find dy over dx at the point 1, 2, which means we plug in 1 for x and 2 for y. So we get negative 4 times 1 over 2, which is negative 2. So that's my slope. So I come over here, my slope is negative 2. Now we just plug it in. So y minus 2 equals negative 2x minus 1. And that's our equation of our tangent line to my ellipse at the point 1, 2. That's it. So it's basically the same thing we've been doing with tangent lines with regular functions. We're just, when we find the slope, we have to take the derivative implicitly. Okay? So now the second one. Again, this is an assignment. This is something we've done before, where we find the derivative, we find the tangent line, we find the normal line, we graph all three so we can see what it looks like. Okay, so I've got this circle. They've given me this equation, x squared plus y squared equals 25. So that is a circle with its center right here at the center with a radius of 5. So 1, 2, 3, 4, 5, negative 5, negative 5. So basically my circle looks like this. Okay, and we're finding at the point negative 3, 1, 2, 3, 1, 2, 3, 4. So this is where our tangent line and our normal line are going to be. Okay, so before we can do anything, we need to find the slope. Okay, so again, we take the derivative of this with respect to x. So dy over dx, that's going to give me 2x plus 2y dy over dx equals 0. Solve for our dy over dx, which equals negative x over y. Okay, so our tangent line. So our tangent, again, we're using this equation, y minus y1 equals m times x minus x1. Okay, so our tangent is going to be y minus y1, which is 4, equals the slope, and the slope I plug into here, this is my m, and I plug in -3 for x, so I get +3 and 4 for y, x plus 3. Okay, and then for our normal line, which is the same equation, y minus 4 equals, but then the slope is the same as the tangent. It's this one, but we change the sign, so it's going to be negative, and we take the reciprocal, so it's 4/3, x plus 3. Okay. So again, both of these have the same point, -3, 4. So for the tangent line, this is my point. It has a slope of 3, 4. 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. So this right here, that's my tangent line. My normal line has a slope of -4, 3. 1, 2, 3, 4, 1, 2, 3. 1, 2, 3, 4, 1, 2, 3. And that's my normal line. And notice they are indeed perpendicular to each other. And that's it. So we're just doing the same stuff we've done before with regular functions, finding the normal line, finding the tangent line. But this time, to find the slope, we just have to take the derivative implicitly.